So I start. Welcome everybody. So I'm I'm Nejat Fad. I'm here on behalf of Professor Burns to as a session chair. This session is about leg locomotion. The first presentation is from Yue Zhao. About the title of the presentation is Adaptive Gait Parameters Adjustment Strategy for a Hexapod Robot Walking on Stairs Based on 3D Terrain Perception. You can proceed.
Okay, thank you. Good morning, everyone. My name is Zhao Yue. I'm a student in Shanghai Jiaotong University in China. So it is my pleasure to introduce you our paper. The title is Adaptive Gait Parameters Adjustment Strategy for Hexapod Robot Working on Stairs Based on 3D Terrain Perception, where compared with the wheeled robot and tracked robots, legged robots have advanced potential to help people in daily life. One major reason is that there are many steps and stairs in human's life. So I'll introduce our people. So we proposed an online perception-based stairs climbing planning method. I'll introduce it from 4 aspects. First, I'll show you our robot, and then I'll explain the method we used. After that, I'll show you the experiment. And at last, I will talk about the future work. So let's see our robot. The robot is called Qingzhui. It is a name of we named it with a house name a famous house name in Chinese history. The robot is about 1.4 meters long, and the width is about 0.8 meter, and the height is about 0.5 meter. So Qingzhui has 18 encoders, 18 tank sensors, and 1 IMU as proprioceptive sensors. It has 1 lidar and 2 IGBT cameras as perceptive sensors. It can work at about 1.5 meters per second. So let's see the leg structure. Each leg has 3 motors. The degree of freedom is 3, and with the data from the encoders and the tank sensors, we can calculate the position, the velocity, and the force of each tip. In our early work, the robot we proposed an online force-based gait planning. In this video, the robot first trot on the flat plane, and then it will work on the stairs. The payload is 18 kilogram, and the robot weighs about 50 kilogram. So now the robot works on the stairs. In this gait planning, there is no vision information, so there have some problem. Also, there are some problems. Okay, so what are the problems? What the problems are? The first one is the interference. So you see, if this is the stair and this is it, and this is the leg, we want the leg steps on the stairs. But without vision, sometimes there may have some collision like this. And the second problem is the workspace. In the right picture, you see 5 tips are on the first floor, but the back tip is on the second floor. In next step, the back leg will step on the fourth floor, so it may get out of the workspace, and this situation may lead to the falling down of the robot. To solve these problems, we proposed an online perception-based stairs climbing planning method. There are 3 things we need to do. The first is we need to know the robot's position and pose. So we need the state estimation, And the second thing is that the robot needs to know where the stairs are and what shape is it. So we use the IGBT camera to model the stairs. And after that, the third thing is we need to calculate the right gait parameters. Each stance leg has a feasible area, so we need to use intersection computation to get the appropriate gait parameters like step length or step height. So although we can use IMU to calculate the robot state, we use the forward kinetics to as another source. In our gait planning, there are always three tips contact with the ground, so we can calculate these three stance tips positions in both in the body coordinate system and in the ground coordinate system. So based on that, we can get the pose and position of the robot. So after we know the robot state, we need to model the stairs. We get the depth image in front of the robot with a IGBT camera, and then we transfer it into the point cloud. We use the ICP method to combine each frame and model the stairs. After that, we segment the horizontal plane to model the stairs. And after we know the relationship between the robot and the stairs, we need to get the right step length. To avoid the collision, we model the scene as one cylinder, and we model the terrain as cylinder size, so we can calculate the distance between the same cylinder and each terrain cylinder. So we can, based on that, we can decide this foothold position is safe or not. Our work is to avoid situations in the figure C and figure G. So now let's see our experiment. We use an Intel IGBT camera to model the stairs. The robot steps climb the stairs step by step. The distribution of legs is much better because the leg can step only one stairs in this experiment. And sometimes you can see the robot may walk back because it adjusts the workspace for the next step. Okay. Okay, now the robot walks down the stairs, and from this image flows, we can see we solved the two problems we proposed. There is no collision, and the robot is much sleeper. And this is the experimental data. The black line is the trajectory of the body center, and the colorful lines are the tips trajectory. So, where in future we not only want to change the gait parameters, we want adaptive foot selection, because in some complex terrain, the safe area is discrete. So the robot needs to select the foothold area adaptively. Okay, that's all. Thank you for your listening.
So thank you, Zhao, for the presentation. Anyone have question? I think Jiang, you can continue. Yeah.
Can you hear me?
Yes, we can hear you.
Yeah, okay. So thank you very nice presentations. So I have one question because I see the structure of your hexapod. So basically it's a little bit different from the classical hexapod because I found that the structure is you have quarter peg plus two legs in the front part of the lower or the front and the real part of the lobo. Have you ever compared this kind of the new structure compared to the classical hexapod lobo? Like each side has the three legs. What is the benefit of this kind of the new structure?
Okay, thank you for your question. Some animals may have this angle in the direction of gravity, where we in this this setup the robot can work more straight. So the speed is much better than another setup, and you know six legs robots. One major advantage is that it can the payload is much better than four-legged robots, and this leg structure makes it possible. And if you the best the most thing we think is in this structure, the robot can work more speed, can work faster.
Okay, I see. Okay, thank you very much.
Okay, thank you.